If you want to protect your brain against aging, popular wisdom says you should challenge your mind. Do a daily crossword, learn a language, keep the mental gears turning. But solving a puzzle on Sunday morning does not trigger the sweeping structural adaptations required to fortify a decaying neural network. For decades, neuroscience has struggled to define what actually drives meaningful plasticity in humans. There is a long-standing joke in the field. If you desperately need a thesis, study the effect of any compound on a subject's sleep cycle. It is incredibly easy to disrupt REM sleep with a minor chemical tweak. Because the system is so fragile, it makes a terrible benchmark for measuring profound neurological intervention. The same illusion appears when studying memory at the microscopic level. In an isolated Petri dish, you can drop a random molecule onto a few neurons and immediately trigger long-term potentiation, the neural firing pattern associated with learning. It is remarkably easy to tilt the scale in a closed, controlled environment. But a few extra firing neurons in a lab dish or a mouse running on a wheel do not directly translate to the human brain. When researchers attempt to use these tiny single-molecule interventions to stop actual cognitive decline in older adults, they fail. The human body does not adapt its macrostructures based on a microscopic chemical nudge. To physically alter the architecture of a living, aging brain, you have to demand it. You have to deploy a massive systemic cascade of interacting molecules that isolated tweaks and crossword puzzles simply cannot produce. The most effective triggers for this biological deployment are highly complex motor movements. Physical exercise forces the body to release the dense molecular cascades required for true structural plasticity. We used to view exercise as a secondary benefit for the brain. The assumption was that getting your heart rate up improved general metabolic health, increased blood vessel growth, and the brain passively benefited from better circulation. However, that old view is completely outdated. Modern research shows that exercise is a direct mechanical trigger for neuroplasticity. More importantly, cardiovascular training and resistance training are completely distinct biological inputs. Their internal physical mechanisms do not overlap. These two separate physical demands target entirely different macrostructures inside your head. Aerobic work specifically rebuilds the outer, wrinkly gray matter, while heavy resistance training fortifies the deep internal gold-hued wiring known as white matter. If you treat all exercise as biologically redundant, choosing only to jog or only to lift weights, you are leaving massive, critical regions of your neural anatomy completely vulnerable to decay. Let's isolate the outer layer first. The brain's gray matter wraps around the exterior cortex and extends down into deep regions like the hippocampus. When you engage in mild to moderate aerobic exercise, like a continuous 20 to 30-minute run, you are providing the exact mechanical trigger required to stimulate this specific tissue. That sustained rhythmic output forces your body to produce and release specific molecules, primarily lactate and a protein called BDNF. These streams travel into the brain and flood the gray matter. This localized biochemical influx actively maintains and expands the physical density of the hippocampus, directly enhancing your capacity for spatial processing and long-term memory storage. Aerobic training is the ultimate protector for your brain's hardware, but fixing the hard drive does nothing for the cables connecting it. The aerobic pathway entirely ignores the brain's internal communication network. Beneath the gray matter lies the white matter, the dense internal connective tissue that links different regions of the brain. In humans, this network is massive, making up roughly 60% of the brain's mass. Zooming into the cellular level, we find its structural core, myelin sheaths. These fatty layers tightly wrap around individual nerve fibers, or axons. The physical thickness and integrity of these myelin wrappings are not just protected. They dictate the precise speed electrical signals conduct across your brain. If gray matter acts as the memory storage bank, your myelinated white matter dictates processing speed. It controls how fast you can retrieve a memory, make a complex decision, and execute a physical action. Here is the critical biological gap. The aerobic exercise that floods the brain with BDNF does almost nothing to fortify this myelin. Maintaining processing speed and executive function as we age demands a biological input that targets the internal architecture specifically. That missing trigger is resistance training. Pushing or pulling heavy physical loads provides the precise mechanical stress required to force the white matter to adapt. Instead of BDNF, muscular exertion drives a massive release of a different hormone, IGF-1. This molecule is the primary mediator for white matter adaptation, binding to and fortifying the myelin sheaths. We know that IGF-1 is critical for the initial creation of white matter in the womb and during infancy, but maintaining high levels of this hormone is biologically necessary to preserve that architecture throughout your entire lifespan. To trigger an effective IGF-1 release, the movement demands multi-joint compound mechanics. You have to recruit multiple large muscle groups simultaneously, using movements like a heavy leg press or a chest press. You do not need to lift to absolute failure. The established protocol for neurological benefit is roughly 80% of your maximum effort, completing 3 sets of 8 to 12 repetitions per exercise. Completing this protocol over just 20 to 30 minutes triggers an immediate acute bump in your baseline cognitive function, similar to the short-term focus you get after a run. But acute focus is not structural change. To physically thicken the white matter tracks, the system requires chronic pressure. The literature shows you must maintain this resistance protocol 2 to 3 times a week for a minimum of 6 to 12 months. Moving heavy physical loads on a chronic timeline satisfies a fundamental engineering requirement for the structural integrity of your brain's internal wiring. Observing the aging process shows the cost of ignoring this pathway. Decades of neglect cause the biological network to fragment and turn brittle. Without regular mechanical stress and the resulting IGF-1 repairs, you begin to develop what neuroscientists call white matter lesions. These are areas of localized structural damage that form deep inside the brain, typically clustering around regions of poor blood flow. As lesions multiply, signal conduction across the myelin slows down, causing a steep, measurable drop in your executive decision-making and overall processing speed. In fact, the physical decay of your white matter structure stands as one of the most accurate, independent predictors of age-related cognitive decline. This network degradation happens completely independently of standard Alzheimer's markers. Even if you lack the genetic predispositions for amyloid or tau plaque buildup, a neglected white matter network will still fail. Dementia is simply the final stage of this decline. Waiting for a clinical diagnosis before you address your brain health is like waiting for end-stage diabetes before you adjust your diet. By the time symptoms appear, the structural damage is already deeply entrenched. Strict long-term adherence to the resistance training protocol actively pushes back against this decay. The chronic release of IGF-1 repairs myelin and actively halts the spread of white matter lesions. When we take that resistance pathway and place it next to the aerobic BDNF cascade, we finally get a complete biological model. Cognitive resilience depends on a 2-part engineering solution that leverages a dual-modality physical prescription. You cannot swap protocols. Cardiovascular work protects gray matter. Resistance training protects white matter. There are no shortcuts and no single-molecule fixes. Optimal brain health is achieved only when you mechanically force your body to deploy both molecular arsenals, decades before the decline even begins.